started talking about our oxidation reactions and our reduction reactions. So we looked at some reducing agents. And so far we've talked about our three main reducing agents we're going to be looking at: sodium borohydride, H2 platinum palladium or nickel, and lithium aluminum hydride. With our H2 platinum palladium or nickel, it's going to reduce pretty much everything. So we don't have a lot of selectivity. So depending on what reagents we start with, we want to consider that. So our H2 platinum palladium nickel will reduce all carbon oxygen pi bonds and carbon-carbon pi bonds. And that's going to be really important. Sodium borohydride, we looked at and we talked about it reducing aldehydes and ketones, but it's not going to reduce carbon-carbon pi bonds, and neither will lithium aluminum hydride. But there is a big difference between sodium borohydride and lithium aluminum hydride in their reactivity, so we need to discuss that. So our hydride reducing agents can be somewhat selective because our two different hydride reducing agents, the main ones that we're discussing, have different reactivities. So both sodium borohydride and lithium aluminum hydride will not reduce carbon-carbon pi bonds. So it's a much better option if we don't want to reduce a carbon-carbon pi bond. You must know the difference in the selectivity. H2 with our metal catalyst is going to reduce both the carbon-carbon pi bond and the carbon-oxygen pi bond. So this is better if we want to retain our carbon-carbon pi bond. So you can see the difference in our product. And that's a big difference with our reactivity. And again, the reason why is because of our catalysis with H2 and the fact we're usually using high pressure. That means that we are putting in enough energy to reduce all of those. But sodium borohydride and lithium aluminum hydride, we don't have any partial positive charge on our carbon-carbon pi bond, so they're not attracted to that. And remember, here, that hydrogen is a hydride. So our pi bond cannot act as a base because we do not have a partial positive hydrogen in this substance. We're reacting it with a hydrogen base or a hydrogen nucleophile. It is not an acid. We don't have a partial positive hydrogen. But we do have a difference in reactivity between our two. So remember, just because our boron and our aluminum have a negative charge, that doesn't change its electronegativity and its partial charge. So our aluminum is a metal, and it has a pretty strong partial positive charge, whereas our boron is considered a nonmetal, though it is still more electropositive than hydrogen, because hydrogen has about the electronegativity of carbon, and boron is to the left of carbon on the periodic table. So in both cases, what we have is a partial negative hydrogen. Again, this is very different. Oh. This is very different from our partial positive hydrogens, because this now means that our hydrogen has a negative charge, or a partial negative charge. But of the two, our sodium borohydride has less of a partial negative charge because boron isn't as electropositive. Remember that difference in polarity has to do with how big of a difference in electronegativity we have. So we don't have as big of a difference in electronegativity with our sodium borohydride. And as we discussed before, the less reactive, the more selective. So sodium borohydride isn't as reactive because we don't have as big of a partial negative charge. We already see the difference in reactivity when we just look at putting in our reagents. Notice sodium borohydride can be mixed with an alcohol or water, but lithium aluminum hydride cannot, because we have a stronger source of H negative in lithium aluminum hydride, and it will react violently with water, and then we will not get any reaction because we won't have any hydride left. It'll all react with water. So knowing that difference in reactivity is important, and putting a 1 and a 2 in these positions are very important for lithium aluminum hydride. You cannot mix this with water. So what that means is that we can have a difference in reactivity. We can also have a difference in reactivity by varying our R groups. We won't be doing that as much, but we can, and that can help to give us even more selectivity. by utilizing our sterics. So that's also something we can do. So because lithium aluminum hydride is more reactive and it's less selective, what we actually see is lithium aluminum hydride can react with things like esters and carboxylic acids. Now our partial positive of our carbon and our ester and our carboxylic acid is more partial positive, but for that full reduction to occur, we have to have a leaving group. And in the case of carboxylic acid, that leaving group is water. And in the case of our ester, that leaving group is this OMe. So this is our leaving group. To force an oxygen to leave, we need a strong hydride agent, because otherwise our leaving group won't leave. So with our lithium aluminum hydride, it's strong enough to force out that leaving group. But sodium borohydride is not strong enough to force out that leaving group, so we don't get any reaction with sodium borohydride with esters and carboxylic acids, because we can't force a leaving group out. Again, here, our leaving group. So it's generally not strong enough. So sodium borohydride will only reduce aldehydes and ketones. Lithium aluminum hydride will reduce aldehydes, ketones, and carboxylic acids and esters. And our H2 platinum palladium nickel will reduce any carbon-carbon compound because we're really redundant. Notice in both our ester and our carboxylic acid case, we're reducing to the primary alcohol because, again, we're losing this group. This is our leaving group. Looking at that mechanism, it's fairly straightforward. We have our strong negative charge in our hydride. Remember, hydride is also a base, so we consider this basic conditions. We will not form a positive charge. Then we will reform our carbon-carbon double bond. To form this, plus. And this is a step where you need that strong reducing agent. Because to force this out, we need to really have that forward reaction driven. Because this is a stronger source of H negative, even though our oxygen with a negative charge isn't very stable, this is less stable. Then, of course, we need another amount because we're going to get that second attack of our hydrogen nucleophile. Notice also I didn't protonate my alcohols yet. That's the last step in the mechanism, but that can't happen until the reaction is complete because we do not add water until after the reaction is complete. So I don't want to see these things protonated until the last step of the mechanism, because up until all this is formed, you will not have any water present. So you don't have any source of H positive to protonate those alcohols. If you did, you wouldn't get a reaction because water would just react with lithium aluminum hydride instead of reacting with your ester or carboxylic acid. Also, I don't have this attacking and that leaving in one step because remember, an SN2 reaction does not happen at an sp2 carbon. So instead we go through this tetrahedral intermediate, meaning a carbon that's tetrahedral. Sodium borohydride doesn't have a strong enough hydride source to force this reaction to occur, so we don't get any reaction. And of course, our H2 with platinum, palladium, or nickel, we force it to happen. So we do need two hydride equivalents, and this is just the mechanism that I just went through. And then the last step is going to be the protonating of our negative charged oxygen, but that doesn't happen until the last step because until the last step, we don't have any water present. in the lab, we would react this for a certain amount of time, let's say 2 hours or whatever, until we check and make sure the reaction is done. Then once we're sure that the reaction is complete, then we'd add water and the protonation would occur. Not until, because again, we're not adding water to the last step, or it would just react with our hydride agent. So this is just a summary. Notice that our sodium borohydride and lithium aluminum hydride will both reduce aldehydes and ketones. Neither will reduce carbon-carbon pi bonds, but lithium aluminum hydride is strong enough to reduce carboxylic acids and esters. You must know the difference between these reactivities. You must know these selectivities with your different reagents. So this is just a summary of what I just talked about. So looking at this example, we're reacting this with sodium borohydride and H2O. Oh, one thing I wanted to note, none of our reagents will reduce aldehydes over ketones or ketones over aldehydes. So if you're reducing a ketone, you're reducing an aldehyde as well. We don't have any difference in reduction for those. You can use bulky R groups to sometimes, on our lithium aluminum hydride or sodium borohydride, to maybe get your aldehydes to reduce more because of less sterics. But overall, from these reagents, if it's reducing aldehydes, it's reducing ketones as well. And all of these will reduce both. So we don't have any selectivity between aldehydes and ketones. At least not at this point in our discussion. So looking at this example, first thing, note what you have, what functional groups you have. You have an alkene, a carbon-carbon pi bond, you have a ketone, and then you have an ester. So with our first functional group, we have our sodium borohydride and water. Those two things can be mixed. That's perfectly fine. And our sodium borohydride is our hydride reducing agent. We will not touch the pi bond. We also will not reduce our ester. It's not strong enough, but we will reduce our ketone to a secondary alcohol. So that's our intermediate compound. Next, we're reacting it with lithium aluminum hydride. And this, you might see water, you might see H3O+. Both of those are a source of proton. It depends on what you're doing. The big note is lithium aluminum hydride is not being mixed with H2O or H3O+. That's being added after the reaction is complete. So again, we will not do anything to our carbon-carbon pi bond, but now we can reduce our ester. Here's our leaving group. So this bond is going to break, and we're going to form this primary alcohol. But of course, it's still going to be attached because we're not doing anything to this point of the molecule. So what we get, where did that come from? We still have 6 carbons. This is our leaving group. And our carbon-oxygen double bond is reduced to primary alcohol. They're both protonated because that's what the water does. You will not isolate a negatively charged carbon. Oxygen. Well, you won't isolate a negatively charged carbon either, but you won't be getting a negatively charged carbon. So looking at these from last week, here we have H2, platinum, palladium, or nickel. This is platinum. That's going to reduce all pi bonds. So we're going to reduce our carbon-carbon pi bond, our ketone, and our aldehyde. We're going to reduce all pi bonds. If we look at sodium borohydride and water, we're not going to reduce carbon-carbon pi bonds. There's none in this example. But we do have a ketone, and in this case a carboxylic acid. our sodium borohydride is not strong enough to reduce the carboxylic acid, it will only reduce the ketone. And lastly, here we have our lithium aluminum hydride followed by water. That's going to reduce both our ketone and our, in this case, ester. This is our leaving group. So our answer is D. We reduce both of those. This is not being shown, but of course you're also going to have what's left of the leaving group in your final product. That's easy to remove because ethanol has a pretty low boiling point, but if I ask you for all products, I will want to see that leaving group. So that's our difference in selectivity of our reducing agents. And again, we're reducing that carbon. Of course, the hydride agent is being oxidized, but we are reducing the carbon. So that's where we're talking about reduction. We're usually describing our carbon. As far as forming diols, we also know routes. And just like before, if we have multiple alcohols in the parent name, it's going to be diol. If we have 3 alcohols, it'll be a triol. We don't see triols as much. Diols are found in nature a lot, so we're focusing a little bit on it here. So these are just 2 diols, and the only difference with our name is we're going to have di in the name, and we do have to specify where both oxygens are on our parent chain. Because of course they could be anywhere on our parent chain, so we need to specify that functionality. Again, just like before, the 1,3-propane diol can also be propane 1,3-diol. That's also acceptable. So our position of our hydroxyl groups are identified as locate numbers before the parent. And of course, if it was a triol, you'd have 3 numbers. So really no difference with our naming. There are some common names for diols, so you do need to know these too. Ethylene glycol is the same as our 1,3-propane, or actually 1,2-ethane diol. Ethylene glycol is found in a lot of materials you use. Things like shampoo, well, usually conditioner, and you'll also see it in eye drops. So ethylene glycol is used a lot in common products. Propylene glycol as well. You see that. Read the back of a couple of things in your bathroom. You'll probably find ethylene glycol and propylene glycol listed often. So, yeah, you definitely don't want to drink ethylene glycol. It won't make you feel very well. That's why you don't want to drink eye drops. It'll make you a little sick. So you gotta be a little careful. But you'll see those. So you need to know those common names. As far as preparation of diols, we've talked about a couple of routes. We can do our anti-dihydroxylation. That's going through forming the epapside. We also know our syn-dihydroxylation with our osmium tetraoxide and NMO, or cold KMNO4. That's another route we talked about that both does syn-hydroxylation. Of course, if we start with 2 ketones or 2 aldehydes, we can form a diol with these reducing agents that we just discussed. So we can form diols that way as well. The next reaction we're going to talk about is reacting our C double bond O with a carbon nucleophile. So the next reaction we're going to talk about is called the Grignard reaction. The Grignard reagent is named after one of the first scientists to report on this particular reaction. It's what we call a name reaction. The name doesn't really mean anything except it's after someone. But you do need to know it because it's known so much. If you see this reaction on the MCAT, it might just say Grignard reaction, and you need to know what it means. So there's some name reactions. I'm not a big fan of name reactions because the name doesn't tell you anything, but you have to know some of them because they're used so widely. So the Grignard reagent is used because, one, you'll form alcohols in this reaction, and two, you're going to form a new carbon-carbon bond. This is the second reaction that we're going to talk about so far in this class that forms a new carbon-carbon bond. Now, every time we're talking about forming a new carbon-carbon bond, we need a carbon nucleophile. The other reaction we talked about is deprotonating a triple bond hydrogen and forming that carbon nucleophile because the triple bond carbon can stabilize a negative charge better than a single bond or a double bonded carbon. Still very reactive. So here we're going to form a carbon nucleophile in a different route. So if we have an alkyl halide, it can be any alkyl halide. We just need a carbon bonded to a halide. Chlorine, iodine, bromine, most common. Not so much fluorine. We don't use fluorine a lot. Then we treat that alkyl halide with a magnesium metal. And this is key for this. If we don't have magnesium metal, this will not work. So the magnesium metal will insert itself between the halogen and our R group. And now we're going to form a carbon nucleophile. We won't have a carbon nucleophile until this magnesium metal inserts itself. It will not exert itself between a carbon and a hydrogen. It has to be a carbon halogen bond because it has to be that very strong polar bond. So remember, in our carbon halogen bond, our carbon has a partial positive charge and our halogen has that partial negative charge. However, once the magnesium inserts itself between, then now we have a metal bonded to an R group. So our metal is more electropositive. So now we have a partial negative R group. Now magnesium is partial positive enough where that bond between R and Mg is kind of at that little, the area where, remember we talked about in Organic 1 and a little bit in General Chemistry, how we say an ionic bond and a covalent bond, and really what we're looking at is a difference in electronegativity, and at some point the electronegativity difference is so big that instead of sharing electrons, we have a positive charge and a negative charge. But somewhere in between, there's some haziness. So this bond is one of those haziness where you can think about it as a very, very, very polar covalent bond, or as an ionic bond where the metal has a positive charge and the carbon has a negative charge. Both ways to think about it has that carbon with that negative charge. So it's kind of at that hazy area. It's often drawn like this, like a covalent bond, because magnesium is one of those metals, those transition metals, but you can draw it as the R negative Mg positive. So this can work with any R group. We don't have limitations. Remember, our limitations before we could form our negative charge in our triple bond, well, we had to have a triple bond. Otherwise, we couldn't form that carbon nucleophile. Here, the carbon can be a double bond, it could be a single bond, it could be a triple bond, but usually that's not done because it's not necessary. You have a route with a triple bond already. It could be primary, it could be secondary, it could be tertiary. So here we have a bromine connected to a carbon of a benzene ring. The magnesium can insert itself, and you could think about it as having that positive and negative charge. Now, key, do not add a carbon. There is no carbon. There's 6 carbons in this molecule of the benzene ring. Don't add an extra one. There's still only 6 carbons. The carbon, that sp2 carbon, is the carbon nucleophile. Here we have a primary, and we can form, again, that carbon nucleophile. So the magnesium atom is being reduced in this reaction because it's gaining more electrons, but that's just looking at its oxidation state. It's because the halogen is still donating a bunch of electrons towards it. So you have to have that RX bond. That's the key. You have to have a halogen. So you can think about it as a very strong partial negative carbon, or you can think about it as a carbon with a lone pair, so a carbon nucleophile. And this is the way I usually draw it when I draw my mechanisms. Again, don't add extra carbons to this. However many carbons you started with your alkyl halide, that's how many carbons your Grignard reagent is going to have. So now we have a carbon with a negative charge. That's not a very stable carbon. It's a very reactive carbon. It's going to react with a lot of things. How can it react? What ways it can react? We have a carbon with a lone pair and a negative charge. How can it react? It can react as a nucleophile. How else can it react? As a base. That's really, really important. This is very basic. It's very nucleophilic. Remember, the more reactive something is, the less selective. So you have to be very careful what's in this reagent. This reagent is so sensitive to water that we probably can't really do it here because we have too much water in our atmosphere. As soon as we form a Grignard reagent in Louisiana, especially today, it would react with water in the atmosphere and no longer will do anything. So you cannot have water, you cannot have an acidic proton, even a slightly partial positive hydrogen anywhere near this reagent, or it will just act as a base. And once it acts as a base, it loses all reactivity. And that's very, very important as well. So the carbon atom is not stabilizing the negative charge. It only forms because of magnesium being a metal. Otherwise, we won't get it to form. So it will act as a base or a nucleophile. In its route of acting as a base, we just have an R. As a nucleophile, we have an R and a negative charge. It's going to react with a partial positive carbon very easily. Now, this won't react with other alkyl halides as well, and I'm going to tell you why in a second. But it will react with a carbon-oxygen double bond, and later on we'll also learn it'll react with an epoxide very efficiently. But otherwise, this is all it's going to react with. So we have a very partial positive carbon, and we have our partial negative oxygen. And remember, this is a strong base as well as a strong nucleophile, so we're not going to form any positive charge in our mechanism because we do not form positive charge in basic media. If we had any positive charge, the R group would just react with it, so that's not going to happen. So we're going to get attacked, pushing the negative charge onto the oxygen, and that's pretty much our reaction. Notice we form an O negative. To work up this reaction, we're then going to throw some water in there, and that's going to protonate our alcohol. Now, water cannot be added until this reaction is complete, because if water is added before this reaction is complete, our R negative is not going to react with our partial positive carbon. Instead, it's going to react with water. So, if it reacts with water, look at our pKa of water is about 15.7. Look at our pKa of an RH. If this is an sp3 carbon, the pKa is about 50. So the forward reaction is highly favored. In fact, this would be a non-reversible reaction because there's no way that our O negative is going to deprotonate the hydrogen of RH. We already talked about that. We need a strong base like NH2 even to deprotonate a triple bonded carbon. The other thing to notice is once this reacts with water, this has no reactivity. Before we reacted it with the Grignard, with the Mg, we at least had an alkyl halide. Now that we reacted it with water, we don't have any reactivity. Remember, this won't react with anything, except for we can give it another alkyl halide by going through our radical bromination, which is not necessarily easy to do, especially in this case. So, once it comes into contact with an acidic hydrogen, we no longer will get any reaction possible. Our reagent is used up and no longer useful. So we have to be very careful that no partial positive hydrogens are anywhere in our other reagents, in our R group, in our carbon-containing compound is attacking, or as water or alcohol in our reaction. So we can't do these in solvents that have an acidic proton. We can't do this in alcohol, we can't do this in water. This is typically done in ethers, and we'll talk about ethers in the next chapter in a lot of detail. So ethers, diethyl ether being the most common, has polarity but no acidic hydrogen. So this is the solvent that these reactions are commonly done in. Again, this reaction is kind of hard to do down here because we always have a lot of water in our air. Works a lot better in places like Arizona that don't have humid temperatures. That's how sensitive this reaction is to water. So when you write this reaction, you draw this mechanism, water is never added to the end. It always has to be 2. You have to be very careful. So there are some things we do to try to get atmospheric moisture out. We might use, instead of air as our media, we might instead remove all the air from our reaction and instead put something like N2 gas or argon gas that has been passed through a drawing tube. That way our reaction isn't in the presence of our regular atmosphere. But again, down here, it's even hard to get all of the water out of our gases like argon. So even that's really hard to do. And as well, you have to flame dry your glassware to make sure there's no water. It's very sensitive to water. Once there's any water present, a small amount, this reaction will not occur. So you have things like a dry box, but sometimes that's more trouble than it's worth, where the whole box has been evacuated and has an inert atmosphere, and you're never introducing anything from outside into it without first being evacuated of all air first. Still, they're pretty hard to work with because of that, so sometimes it's not very helpful. So once we have our Grignard reagent, which we need our magnesium, then we're having that carbon nucleophile, and what we're going to react with is carbon-oxygen double bonds. Now, of course, not carboxylic acids. Why not? A carboxylic acid, as it says in the name, is acidic. That's even more of an acidic hydrogen. That's a pK of about 4. So the Grignard would just deprotonate the OH. So this can't be done in the presence of carboxylic acids because our Grignard reagent is too much of a base. And remember, it's easy for it to be a base because when it's attacking our carbon here as partial positive, there's some sterics. But when it's deprotonated, hydrogen's really small. There's not usually a lot of sterics to that. So what we see is we don't have too much of an issue, a barrier, with our carbon nucleophile deprotonating. So if there is any acidic proton, it's going to deprotonate that first. With our ketones or aldehydes, we're going to get an addition, and of course that's going to form alcohol. And we're adding a new carbon-carbon bond. Notice 1 and 2, that's very important. If you don't put the 1 and the 2, I will remove points because no reaction will occur if there's no 1 and a 2 there. You cannot mix your Grignard reagent in water. Water is the source of the proton to protonate our OH, our O negative after it forms. Here is going to be a very similar mechanism to the one here, but instead of a hydrogen nucleophile, it's going to be a carbon nucleophile. So everything's the same with this mechanism, except this is now an R group. So what we'll get is, with this one, because we have the leaving group, 2 additions of our R group. It's really hard to stop here with just one equivalent, and we'll talk more about that in chapter 21. So it's really hard to stop in this position, at least with our Grignard, because our R negative is so reactive. So if we don't have excess, then we're just going to get a big mixture of this and some starting material. So to get it to go to completion, we have to use excess. It's really hard to stop at that middle position. We will talk about a reagent later on that can stop here, but this is not it. And again, this won't react with carboxylic acids because we just deprotonate our carboxylic acid. So you might think, and this is just a mechanism I drew on the board. You could go through that. Remember, the protonation doesn't happen till the end. You might think, and it's understandable why you might think this, but I'm just going to put it here. You might think that your Grignard, your R negative, can react easily with any electrophile because it's so strong. And that's true, it's not very selective. But if we think about, first off, a tertiary alkyl halide, clearly it's not going to react with that because we won't have an SN2 reaction at tertiary. But even a primary alkyl halide, which remember our other carbon nucleophiles can react with, meaning our triple bond, we did this reaction a lot. We form our new carbon-carbon bond. It's not a double bond. I just want it to be in red. And this is just an SN2 reaction. Now we talked about we can't do this with a secondary because then this would just act as a base and will form the double bond. So you might think that we'll get a similar reaction here. But this is so basic that even with a primary alkyl halide, we're going to get the E2 reaction. Even with the primary. And we're never going to get the SN2 reaction because it's so reactive. So this reaction does not work well even with primary alkyl halides. We need a reagent like this that doesn't have any available hydrogens to deprotonate. If we deprotonate this hydrogen, we don't have a leaving group. So the only possibility is that R group to attack that very partial positive carbon. Here, even though we have a partial positive carbon, we also have a hydrogen that's next to it. So unless we don't have any beta hydrogens, this reaction is just going to act as the E2 reaction. And that's not going to lead to our new carbon-carbon bond. So we don't get this reaction with normal electrophiles. And it's because this is so reactive. This is even more reactive than this. Because remember, our pKa of our triple bond with the hydrogen is around 25. So this is stabilizing the negative charge slightly. This is stabilizing the negative charge not at all. So it's going to do the easiest thing it can do. And the easiest thing it can do is deprotonate the beta carbon. So we won't get any, maybe a very, very small amount of SN2. So this has to react with acetyl bond O. Except for one thing in chapter 14 where we're going to learn it can react with an epoxide. But other than an epoxide and a carbon-oxygen double bond, our Grignard reaction is just going to act as a base. Or find a proton in the atmosphere somewhere. Because it has to have a good electrophile. A better electrophile than our alkyl halides. So even though our triple bond can do it, our R negative can't because it's too reactive. And we're never going to favor SN2. So keep that in mind. Again, the more reactive, the less selective. It's going to do whatever is easiest for it. And the easiest thing, the less sterics, is deprotonating that hydrogen. Ignore this background stuff. Another thing to keep in mind, if there's any acidic hydrogens anywhere, either in our alkyl halide or in our C double bond O containing compound that we're reacting with, this reaction will not occur. As soon as we would form this guy would react with another molecule to deprotonate that, and we would get rid of our carbon nucleophile, just to form an O negative. So we cannot have any partial positive hydrogens. Our biggest problem is OHs. Of course, an NH could be an issue. Those aren't as easily to deprotonate, but again, this is really reactive. It's not stable at all. So any partial positive hydrogen cannot be anywhere near this reaction. So even if our Grignard reagent sort of forms, it's going to react with another molecule OH, and that's just going to protonate here, and we're no longer going to get a have a carbon nucleophile. But there are things we can do if we have a group that already has something like an alcohol on it. So that brings us to, and I'm going to talk about that in a few minutes, but this is just the summary of the reaction. Notice we cannot have an acidic hydrogen anywhere in these reactions, so that's why we can't use a carboxylic acid. A reaction will occur, it's just not the reaction form. So if we're looking at this example and we want to design a synthesis starting from any two compounds, well, through a Grignard, we know we need an alkyl halide and a carbon-oxygen double bond. Remember, there's really no limitations to our Grignard. The biggest limitation, the only real limitation with our Grignard is we can't have any acidic hydrogens. So there's multiple starting materials you can use and it'll all be correct. So first, this is our alpha position. That's where our new carbon-carbon bond formed. Notice we are attacking the alpha position of the C-double bond alpha. So that's where our new carbon-carbon bonds form. So we have these through groups attached, and we can show how each group could be installed with the Grignard reagent. We can start with our C-double bond O containing our phenyl and our ethyl, and then we'd just be adding in our methyl. Again, in this Grignard reagent, make sure you're not putting too many carbons. We're only adding one carbon. This is our new bond, so that's how many carbons we're adding. Or we can have the carbon-oxygen double bond having the phenyl and the methyl, and then in this case our Grignard reagent would be the ethyl. Again, make sure you're not adding too many carbons. And lastly, our C-double bond O can be a methyl or ethyl, and our Grignard reagents could be the phenyl. Again, especially with the benzene ring, students always want to add an extra carbon. There's no carbon between our carbon of our benzene ring and our magnesium. Unless if there should be, but there's not here. Yes?
If you have excess in the first one, would that change it?
No, that's not a good leaving group. It's all about leaving group. So her question is, let's say this is our starting material. If I drew this, and I drew this as leaving, what we'd form is this. It's not a good leaving group. R groups, hydrogens, not good leaving groups. I don't care how much Grignard you add in, you're never going to do more than one addition if you don't have a good leaving group. That's why you need, the ester is a good leaving group, but not a ketone or an aldehyde. With a ketone or an aldehyde, you can only ever get one addition because you don't have a good leaving group. You still have to have a good leaving group to reform that carbon-oxygen double bond. We're still using those same concepts. The only reason why we have a C negative in our starting material is because of this magnesium. Carbon negative will not spontaneously form. It's not easy to form, that's why carbon's not a good leaving group. It will not leave with a negative charge. You have to force a carbon to have a negative charge. All reagents that we ever talk about in here that have a carbon with a negative charge are very harsh conditions. Either a very strong base, deprotonated triple bonded hydrogen, it has to be triple bond. Here, a carbon bonded to a metal. And there's a couple other reactions we're going to talk about where a carbon is bonded to a metal. Those will form carbon nucleophiles. And these reagents are not easy to work with. It's not easy to work with the Grignard. It's easy to draw it in the synthesis. It's not easy to work with. Another very common carbon nucleophile we won't really talk about too much right now, later on, is butyllithium. That's where our carbon is attached to, well, tert-butyllithium is one of the most common. Our tert-butyl, an Li, that forms this carbon nucleophile. A couple of years ago, an undergraduate student died at UCLA from working with this. These are not easy things to work with. This comes in contact with atmosphere, it catches on fire. You have to be very careful when you're removing this from the bottle it's in. You have to have specific conditions. You have to have a syringe where it's never reaching the atmosphere. You have to put it in your reaction. Her syringe came apart, it got on her, she burned to death. These are not easy things we're working with. Carbon nucleophiles are really reactive. So when we draw them on paper, they look real easy. It's not easy to make a carbon nucleophile. You need to have it reacted with something that's so partial positive that we form a carbon nucleophile. Even then, it's very, very reactive. Butyllithium is dangerous. I've never worked with it. You have to take a lot of precautions. And the reason why it's so dangerous is because it's so reactive. So I'm not telling you this is, you won't be using this. We don't use this in organic lab, don't worry. Unless if you go to graduate school in organic chemistry and you're doing very specific things, you might use it. But I just want you to understand how hard it is to make a carbon negative and how reactive it is once you have a carbon negative. You have to be very careful with these. So all of these are routes. They all work. They're all correct as long as you have the right amount of carbons. There's no problems with them. So come up with synthesis to design these two compounds, and then we're going to talk about what to do in the next class if we have an OH present. There are things we can do. We can protect the alcohol so we can do a reaction. So we're going to look at that. So y'all have a great day. Oh, and you can pick up your exams.